Um, Finally, let's talk a little bit about some of the high-level benefits that interoperability can bring to our grids and our systems. So with all that contextual background, right, let's get back to that question of what exactly is interoperability. Now, Chris mentioned our definition earlier. I appreciate it. I have a shorter version of it in the upper left-hand corner. I think that definition is important, but conceptually, I think the most important thing to understand is that interoperability is a tool for unlocking new value across our power system, right? So that value can come from improved operation and efficiencies. It can come from avoided costs due to decreased outages or integration of new resources and the economic opportunities that they bring into energy markets. So in fact, as our grid modernizes, the opportunity to gain value from interoperability grows with every new data stream or communication action. The Gridwise Architecture Council estimated the US power sector could save $10 billion each year through improved interoperability. But we also heard at a workshop we held just in 2018 that a single equipment manufacturer, a single OEM, spends $1 billion a year on integrating non-interoperable devices into their R&D laboratories. And a single investor-owned utility, a single IOU, spends $140 million a year in trying to get new but non-interoperable systems to work together. So when we put it in those terms, and when we consider the economic opportunity that each customer can embrace by integrating their technologies and resources into the system through things like FERC Order 2222, right, the value proposition for interoperability may be much higher than we ever thought previously. Now, the traditional utility approach to interoperability is to decrease the integration costs for new equipment. To be honest, I think that's a very low bar for the value of interoperability. You know, EPRI even published a study on this in 2017. It's the point-to-point standards integration cost framework that they published. But I think that's a very low value. It's a very low bar for the value of interoperability. And perversely, it's one that the typical utility revenue structure actually undermines. I'm not making any statements about Connecticut structure right here, but we can talk about this in generalities, that utilities are often compensated best for capital expenses. And when integration costs are folded into a procurement of a new system or set of equipment, the cost of overcoming non-interoperability between the utility systems becomes a profit maker for the utility. So the structure of a typical tariff, which again compensates utilities more for capital expenditures than for O&M, creates a perverse incentive for utilities to keep their equipment integration expenses high. And while making equipment integrations more expensive is certainly, it is not any utility's foremost goal. I'm not saying that in the least. This incentive structure does mean that the dollars and cents of improving interoperability will also not rise to the top of the utility priority list because they know that they're going to be compensated for the increased expense due to non-interoperability when new systems are purchased. So contrast that to how interoperability enables customers to pursue any number of value propositions, right? By managing their energy consumption and contributions, consumers can pursue environmental benefits, financial benefits, resilience benefits. They can improve their ability to develop new opportunities through collaboration and coordination with others, right? These all require information exchange. And so interoperability empowers consumers to seek and develop their own value-driven priorities. But in this quest to interact with others, interoperability does something more. It's about more than exchanging the typical energy demand or billing data. It's about unlocking the physical capability of equipment to do something more than what it was originally intended to do, right? Let's consider the thermostat, right? The purpose of a thermostat is to control the temperature in a room by actuating an HVAC in response to a measured temperature change. That's it. It is specific in what it measures and it is specific in how it works. Now consider a communications-enabled thermostat that is interoperable with other systems. That thermostat can be used to manage distribution system congestion, preventing circuit overload and improving system resilience. That thermostat can also be used to clean our environment and balance variable generation renewables, timing its on cycles for when carbon-free power is most readily available. Or that thermostat can decrease heating and cooling costs by pre-cooling to avoid peak rates. And if we think about utility equipment, interoperability is a hedge against obsolescence. Equipment that lasts extra long tends to be extra specified, making it even more challenging to have that equipment do anything other than what it was originally purchased to do. So just as consumer equipment benefits by breaking asset specificity, by that thermostat being able to do all these other things, or an electric vehicle that's plugged in, being able to provide ancillary services, utility equipment can be much more versatile and work longer under different operating conditions by enabling communications and interoperability. Using standard communication protocols to support interoperability therefore decreases the likelihood that still functioning equipment will become either a stranded asset or a reason to avoid system upgrades. And in regulation and operation of the grid, the discussions are often couched in terms of winners and losers. But interoperability is unique in that the ability to exchange information in the grid stimulates innovation that tends to benefit all participants. And we discussed that in our one-page case study on data standardization in the framework. And this case study gathers information and data from across the country to buttress this perspective, because often when we talk about it as how interoperability is a win-win for everybody, the argument is one of idea and not one of fact. So we're trying to assign some fact and some data to this discussion. So I do want to take a quick aside to give a little context, right? Let's talk about the role that DERs play on our systems and how interoperability might relate to that topic. So I'm going to use PV inverters and the IEEE 1547 standard as the basis for this discussion. The reason I'm going to do that is that PV inverters are mature in their requirements for interacting with and interfacing with the grid and have gone through a decade of evolution on this, so we can understand some trajectories of how things are changing. In the framework, you can see here that we identified some inverter functions that are either required by IEEE 1547 or California Rule 21. So what's important is to understand that when 1547 was first published in 2003, there was literally only one requirement. It was the first requirement. That only requirement was to disconnect the grid when things went wrong. So if there was a problem on the grid or a problem on the PV side, the only requirement was to disconnect. And in fact, by the time 1547 was revised in 2014, 11 years later, only the first two functions were required. And a few others were suggested as possible capabilities inverters might want to accommodate, but were not required. But by 2018, when we compiled this list, we found 36 different functions that were either already required by standards, including the new 1547, or would soon be required by standards. So we've got grid following and grid forming, voltage support and frequency support. We've got ride through and power factor and normal versus emergency operations, right? And with the wide open communications and data space allowed by the standards, it's not clear to me that we have a complete understanding of how we should best communicate to fully leverage all of these new capabilities, right? So I'm fairly certain that interoperability has something to do with it, because we'll need to find ways to exchange information between devices and systems to observe and manage all of these great capabilities. And, so now let's go back to some of our additional case studies about how investments in interoperability help. A study we published earlier this year demonstrates that even the most basic interoperability investments can lead to an improvement in system operational performance. Right, so we published this study based on Hurricane Irma data in Florida. We used smart meter penetration as a proxy for interoperability investments because of the attendant investments that come along with communications networks to enable smart meters. And we published, a 30-page study on it, NIST Tech Note 2137, the link's on the bottom. But if you don't want to read all of that, there's a one-page case study in the framework where we describe that these basic investments in interoperability reduce the share of outages that should be expected as wind speeds increase during hurricanes.